It's my pleasure to introduce our next seminar speaker, Dr. Donor from GFTL University. Dr. Donor graduated from the University of Chicago with his master's and his PhD in 1983. He spent about 5 years first as a postdoctoral fellow and scientist at National Center for Atmospheric Research. After that, he spent several years as faculty at the University of Chicago at the Department of Geophysical Sciences, and then moved to Princeton University, where he's currently physical scientist at the GFTL. He's also lecturer in the Department of Geosciences and Department of Atmospheric and Aerosol Sensitivity. And he's very well-known climate modeler and manipulation developer. He's written a book in the States with our model, general circulation model, and this journey welcoming
Thank you for that welcome. Thank you, Murat. And thanks to all of you for your interest in my thoughts on climate forcing, climate sensitivity, and perhaps a bit strangely, atmospheric vertical velocities. So let me start out with just a few words of motivation for this. The overarching question with a lot of practical societal implications goes back to the point that uncertainties in both climate forcing and sensitivity limit the extent to which today's climate projections can meet some critical societal needs. And scientifically, this arises because the observed climate transition from pre-industrial to present times depends simultaneously on climate forcing, on climate sensitivity, and also variability. So this precludes the determination of any of those from observations alone. So this is the big picture that I'm going to be operating within. So let me start out with a diagram that probably many of you have seen before, and this is the IPCC Assessment Report 5, Estimates of Climate Forcing. And by climate forcing, I'm referring here to the global mean top of atmosphere radiative forcing change relative to 1750, from let's say about 2015 back to 1750. So if we start out by looking at the one that we're probably almost familiar with, carbon dioxide, this is a greenhouse gas, and it's produced an estimated forcing of about 1.7 watts per square meter from pre-industrial to present day. And I'm not going to go through the other gases, but I want to come down next to aerosols. And aerosols have been a big source of uncertainty in climate forcing. These are human-produced aerosols. And we tend to break it into what sometimes are called direct effects of aerosols. So this is mostly scattering, but from black carbon it could be absorption. And this is thought to produce a cooling of about minus 0.3 watts per square meter. It's this line right here. The big uncertainty that will be a part of my talk involving climate forcing are what here is called cloud adjustments to aerosols. These are cloud-aerosol interactions, changes in cloud properties as a result of aerosols. The estimate of that is about minus 0.6 watts per square meters. It's twice the direct effect of the aerosols. This is sometimes called the indirect aerosol effect. This climate forcing really did not go into climate models in any serious way until this most recent generation of AR5 models. It had been ignored for the most part prior to that. And it's a very difficult forcing to represent. It involves cloud microphysical processes. It's operating, it's leveraging on about a minus 15 to minus 20 watt per square meter cloud radiative effect. So there's a big negative term there, and doing just a little bit to that can make a big effect on the climate. So the interesting part here is the uncertainty on this is very large, going from almost nothing to maybe minus 1.3. And combined with some uncertainties on the direct effect, this leads to a range of almost 2 watts per square meter cooling in the estimated aerosol forcing of the climate system. So notice that actually encompasses the whole CO2 warming effect. So the total greenhouse gas warming, if you take the CO2 and other gases, estimated currently to be around plus 3 watts per square meter. So we have a very strong question about climate forcing. Has it been closer to 3 watts per square meter, or has it been maybe only 1 watt per square meter? So that's the forcing background of this problem. Now let's put that into the context of understanding how the climate has changed from the pre-industrial to present day. So I've been talking about forcing, and here you see a total forcing range. So this is greenhouse gases plus aerosols. Practically speaking, going from about 1 to 2.5 watts per square meter. The dots on this diagram show that forcing plotted against the climate sensitivity. Climate sensitivity is defined here as an equilibrium. How much does the global mean temperature change for a unit of forcing by greenhouse gases, or whatever mechanism of change we might think of. And the dots on here show models from CMIP3 and CMIP5, the climate model intercomparison programs, and where do they fall in terms of their forcing and their sensitivities. And the dots that are highlighted in either red or green are the models that are able to successfully reproduce the climate change that has occurred from pre-industrial to present day. So one of the first things to note is a lot of climate models out there actually can't do that. There's somewhat an impression sometimes that all climate models can do it. They don't all do it. And so the blue dots are the CMIP3 models that don't succeed in reproducing the climate change, and the black dots are the CMIP5 models that don't succeed. But the ones that do are marked in green and red, and the fits to those green and red ones are pretty good. They're the green and red lines. The red is a study Jeff Keel did, mostly CMIP3. This is work that Piers Forster did for CMIP5, and there's a pretty good fit there for the green models. And what you see is those models that can successfully simulate pre-industrial to present day climate change do so by trading off either fairly high values of forcing with a lower value of sensitivity, or they do it with a high sensitivity and a lower net forcing. And so this is the question again, a range of about 2 on the forcing. That's the uncertainty really in the aerosol forcing, which, as I said, could go from anywhere from 0 to -2, and then you add the greenhouse gases on to get the total. So we're somewhere on this diagram if we want to successfully simulate climate change, but it could either be, let me call it, a high forcing, low sensitivity scenario, or a high sensitivity, low forcing scenario. So how it happens is uncertain, and it comes down to, in one sense, the forcing not being known. We also do not know from any first principle grounds what the sensitivity is. So we're stuck on that diagram. Now, why is this so important? This question of how did the 20th century warm? And again, was it high forcing, low sensitivity, or low forcing, high sensitivity, or maybe somewhere in between? Why is that an important question, other than just an academic one? Future climate change will be driven more by greenhouse gases than it will by aerosols. And this is because aerosols have a shorter lifetime. They're rained out, they settle out. That doesn't happen with greenhouse gases, at least not with most of them, like CO2. They just keep building up. It's also likely maybe that aerosols will be regulated by air pollution policy, but even if they're not, the greenhouse gases will dominate in the future. And at that point, the masking, the cooling of that warming by aerosols goes away. And if we want to project, we'll have to know the sensitivity at that point. So this is not just an academic question. It's really important to know the sensitivity. So what I'm going to talk about today is how maybe atmospheric vertical velocities can help to determine the forcing, and rather interestingly, they may also be correlated with the sensitivity. So they may offer a way to find out where we are in this diagram, and they may be able to help on both axes. It's rather interesting. They're also something we haven't paid much attention to in the climate change problem in the past. So this is something which is maybe a new approach. And in science, sometimes we find when we look at things completely differently, we can make some progress. This climate sensitivity uncertainty range has been here since the advent of modern three-dimensional climate modeling in the 1970s. It goes back to the Jules Charney report in the 70s. We've made very little progress on it. Okay, so let me start out with the forcing side of the problem. And my point here is actually going to be a fairly simple one. And it's that forcing from interactions between clouds and human-produced aerosols is a key uncertainty in the current climate models. And that was probably evident on that IPCC AR5 diagram. I hope I've already made that point. But the next one I want to make is that the cloud scale updraft speeds are a major control on this forcing. So this may not be such a familiar point, but I think it's been pretty well established in the literature. But let me show some results that try to make this point in a fairly concrete way. This is a diagram from Reuter et al., and what it's showing in the black contour lines are cloud drop number concentrations. So if we ask how reflective will a cloud be, how much radiation will it reflect, one of the key determinants of that, once we know the amount of water, is how many drops we have. And the number of cloud droplets depends on, this diagram shows, two things primarily: the updraft velocity and the number of aerosol particles. So this aerosol-cloud interaction, there are really two broad pieces to it. Do we change the reflection of clouds by changing aerosols? And maybe do we change the precipitation process and how the clouds organize, how long they last, by changing the cloud drop number concentration? So for aerosol-cloud interaction, and this is an important point not to skip over, one of the most fundamental things we need to know is the number of particles in the cloud. So again, those are the solid lines, and the box over here on the right is just a blow-up of the lower left part of this. Okay, so I want to spend a little time on this. What you can see is that both overall, the updraft velocity and the aerosol particle number are important to determining which of these contour lines we're on. But there is a big regime down here, and this, the red and blue lines are designed to guide your eye. There's a big regime down here where the cloud drop number really doesn't care very much about the aerosol number at all. The functional dependence is entirely on the vertical velocity. And the reason for that is the vertical velocity is determining how fast a parcel of air is expanding, pushing aside its surroundings, and cooling, how much supersaturation is being generated. And that's one of the big controls on whether a drop will form. So this is really basic thermodynamics. There is also a regime where the vertical velocities are higher, where it doesn't matter what the vertical velocity is very much. It's mostly the aerosol number concentrations is important. And then a big regime where both are important. Okay, if we look in most clouds in the Earth's atmosphere, in fact, their vertical velocities are in more like this 0 to 5, except for very strong deep convection. So a lot of our clouds, the problem is knowing what the vertical velocities are. There's been a lot of really great work done on the aerosol particle part of this problem. So Steve Schwartz has been one of the people who's done that over the years. For liquid clouds in particular, I would say we're in pretty good shape. There are some questions about organics and things. Not everything has been solved on this, but I would say we're in pretty good shape on this. In a climate model, we haven't really even started to think about the updraft velocity part of this problem. So this is, in a certain sense, this is very encouraging, because it's starting to say there's a big missing piece that if we can make progress on, maybe we can narrow that cloud forcing uncertainty. It turns out it's not just the liquid clouds where this picture holds, but, okay, actually, before I go ahead, though, I just want to present some evidence, and this is from Andy Vogelman. Some of the really important work on this has been done, really right in this area, Brookhaven. So this is a picture that's very consistent with what I was just saying about dual controls on the cloud drop number concentration. And this is work that Andy did. So it's showing the drop number concentration plotted against CCN at 0.2% supersaturation. And what I'm going to argue is that this CCN is what takes into account the aerosol properties, how big they are, what their size distribution is, and at a specified level of supersaturation, it tells us how many of them are active. But look at how poorly that correlates with the actual drop number in the clouds. Andy is showing these big spreads, and so there's got to be some other parameter than the aerosol properties that's explaining that. And I think we just saw in theory from Reuter et al. What it is. And it's very consistent. Andy broke this down by cloud type. And if you look at this, straightest clouds don't have a very big spread. the biggest spread is the cumulus. And to me, stratus clouds are the ones that maybe have the least variation in their vertical velocities. Cumulus clouds are going to have a big spread. So I actually interpret this as being very consistent with the theory calculations that we just showed. And it clearly indicates, again, this is at least a two-parameter problem. And again, vertical velocity would, based on these very detailed partial calculations we looked at, be the leading candidate. Okay, now, we also see this is true for ice clouds, not only liquid clouds. This is work by Jen Kay and Rob Wood. Same kind of diagram, vertical velocity plotted against aerosol number concentration. They've nicely used color coding to even show how sensitive the number of ice particles is to the number of aerosol particles. And the blue colors are almost no sensitivity. And again, the white lines here are the contour lines for the number of ice particles. What you're seeing, the blue shading, the horizontal lines, up to about 100 centimeters per second in an ice cloud, it doesn't care about the aerosol concentration. Now, there's still a lot of uncertainty on ice nucleation. This is looking at just the process of homogeneous freezing of aerosols, and there are other ways to form ice, but this is a big one, a very important one. Maybe most people would say the most important one, but we'll leave that open. But again, another major cloud type where it's the vertical velocity that's going up and down on this that's the control, not even the aerosol concentrations. And they have observations to support this. In the Inca campaign, they went out and looked, and they found this lack of dependence on aerosol number there, but a big dependence on vertical velocity. So it looks like liquid clouds, ice clouds, vertical velocity is very important. I'm going to actually say that that's the end of my forcing case for now. I'll come back to how we can work on this vertical velocity problem later, but it seems to me these results just scream out. We need to know the aerosol properties, and we need to know the vertical velocities. And what I'll talk about in more detail later is we haven't paid much attention to those vertical velocities in climate models, and where we have, we've made some mistakes in how we've done it. But that's coming later. Okay, so that's the forcing argument. And that's the one, I would say this is a direct cause argument. The vertical velocity is a control parameter very closely tied to the supersaturation, good theoretical basis. Now, the argument that's much messier, and if you'll bear with me, I think it's important because it's messy, but it still offers a lot of promise. This is the sensitivity argument. So not the forcing, but the sensitivity. So this is, let's go to the horizontal axis on that forcing sensitivity trade-off diagram that I showed earlier. And what we are seeing in climate models, and we don't fully understand why, is that entrainment and microphysics in convection are major controls on sensitivity in climate models. And here come the vertical velocities. They both correlate strongly with vertical velocities. These are the more direct controls, but because we're having breakthroughs in measurement of vertical velocity, and again, Brookhaven's leading in a lot of that work, this correlation may be a way to constrain this, and so maybe it's a backdoor into the climate sensitivity. So we may be able to get at both of these problems, both forcing and sensitivity, through vertical velocities. Let me review the literature on this, because I do think this is important. So this is going to be the evidence about entrainment being important as a sensitivity control in climate models. The first breakthrough work on this was published a little over 10 years ago by David Stainforth in Nature. And what we're looking at here are some experiments done with the Hadley Center slab model. And these are a very large number of runs, about 900,000, I think, that were done under climateprediction.net. They asked people all over the world on their PC, do one run of our climate model with a particular combination of parameters in the climate model, different things that are in the physical parameterizations, different combinations. And the colors show how many of those runs with different combinations of parameters there were that produced the different behaviors you see on this diagram. So if only a few of them produced a particular temperature trend, this is the global mean surface temperature we're looking at, then it's got a blue color. If a lot did it, it's got a red color. Red means a lot of parameter combinations produced that result. Blue means only a few did. Okay, so what they did was it was a slab model, so they had a mixed layer ocean with an atmosphere above it, And for about 14 years, they gave the people running this a code that gave them sea surface temperatures, and they calculated the heat fluxes that they needed in the ocean to maintain those sea surface temperatures in the climate. So that's just called the calibration phase. They then let it go with the slab model running with those heat fluxes. They found some combinations, actually the model fell off the shelf. It couldn't even produce the current climate, but not that many. They're blue, but you see those. So they got rid of those. They then doubled the CO2 and looked at what happened. And here's the range of temperature changes they saw. Look, it goes, the dark colors at least go from about 2 up to maybe 7.5. Very much like that equilibrium climate sensitivity range we saw earlier. And you can see they can get that spread in that model just by changing the parameters in their physical parameterizations. So very nice. One model, kind of reproducing what many other models do. That is interesting, but even more so is what parameters are producing that spread, what parameters are responsible for that. So this is showing that spread in changes in the warming in the model. And then this is on the vertical axis, the number of models that get those various changes. So notice most of them are like in the 2 to 6 range. Again, this is that same sensitivity range that I talked about earlier. The whole set is the black line. And the red line, let's look at that one first. This shows what happens if they don't allow their auto-conversion, the way in which the small cloud particles convert into big precipitating rain particles. If they don't change that parameterization, the distribution takes the shape of the red line. It's not very different from the black line, meaning that in their model, that isn't a very important control on climate sensitivity. But wow, look what happens when they let the entrainment change. That's the blue dashed dot line. Huge collapse of solutions. All the high-end ones go away, and the range comes down to just about 2 to 4 degrees. So this was the first big hint that the entrainment parameter in the deep convection was important to climate sensitivity. This, in some sense, is a surprise, because the pretty well-established principle has been that the reason we have sensitivity variation in climate models is because low clouds that reflect a lot of solar radiation change, they respond to warming differently, and we don't quite know how they do it. So once this business about entrainment and convection, deep convection only covers 10 to 15% of the globe. So it's a little strange. This isn't what we would have probably thought of from an observational analysis. And of course, it is a climate model result, so who knows? And we still don't really understand this, but let me take it a little bit further.
Stay with that for just a second.
Yeah.
You're saying when they changed the entrainment, the distribution kind of collapsed into this narrow peak?
When they locked the entrainment, when they didn't allow it to change, it collapses, yeah. So what that says is that, now of course it's a question of what parameter they chose when they locked it, but essentially, yeah, when they lock it, when the entrainment is locked, the variation collapses. So the argument there is that the variation in the entrainment is what produces that spread.
Well,
Yeah.
Okay, but thank you for that. But then, if they were varying the entrainment in the other direction, you would think it would be responsible for part of that curve going off to the left. Not
So
it should be some sense of symmetric change.
Yeah, there's a question of what value, because these are all like partial derivatives, and if you maybe locked it at a different value of entrainment, you wouldn't see that. But the next diagram will, I think, try to address that. So Ben Sanderson. So this was provocative. It was starting to suggest that entrainment was important. But Steve asked one of the questions that you could ask about that. So Ben Sanderson picked that up, and with some apologies for this diagram, but it addresses a little bit what Steve, I think, is talking about. What Ben looked at was the correlation, and using the same data set from climateprediction.net, the correlation between different parameters in the model, and you don't need to know what all these are, but this is showing you nitty-gritty. This, if you work with climate models, you know there's parameters like this that you set. And these are the actual names that the UK model had. And he looked at the various feedbacks, water vapor, albedo, lapse rate, and cloud, and how these parameters vary with it. So this gets a little bit at the question going up or down. So again, the general sense is that cloud feedback and water vapor feedback are especially important ones. Here's the entrainment coefficient, and you see the thing spiking on water vapor, albedo, and lapse rate. It's closely tied to all of those feedbacks in the model. And interestingly, there are big offsets. The water vapor one goes in one direction, and the cloud feedback one goes in the other. So there's the second kind of analysis. The other things that are important in this are cloud feedback related, and there are other cloud parameters. For example, here's the sedimentation rate of ice of ET1, another notorious parameter. So I don't want to say entrainment is the only one, but it's one of the big ones that we're seeing in this correlation analysis between parameters and feedback. And then push this a little further. I'll show one last diagram on this. Let's not really look at the first one. This is looking at various feedback terms and seeing how they depend on the entrainment coefficient very specifically. The first one is just comparing two different ways of evaluating feedback, so let's not worry about that one. But let's start out by looking here on the upper right. So the convention here is, as we go from red, there's not very much entrainment. We go to more than an order of magnitude more entrainment by the time we get to light green. And then some CMIP models, these would have been CMIP 3 at the time this was done, are there in black for reference. So the first one is plotting the inverse of the warming versus the global mean cloud feedback, CRF, cloud radiative feedback. This is showing the standard result that I've talked about before. It gets warmer as you go down. For some reason, this was plotted inversely. But we see this very well-known result that the stronger the cloud feedback is, the more positive it is, the more warming we get. That's the meaning of this thing casting down to the lower right on the diagram. And that's, again, a pretty standard result. Stronger cloud feedback means more sensitivity. But what you see on this, rather interestingly, is that there's this stratification in terms of entrainment. And as we go toward, for a given cloud feedback, we do get a range of sensitivities, with there being essentially more sensitivity down toward the bottom at these lower values of the entrainment coefficient. So and that's suggesting that things other than cloud feedback are also important in this, and that the entrainment is working with that. And the correlation did suggest that, because it was showing, for example, water vapor feedback to be important. So a little more breakdown on this. The cloud feedback has a short wave part and a long wave part. And this diagram looks at the short wave on the vertical versus the long wave on the horizontal. It sees in both the CMIP models and in the Hadley Center model for these different parameters a bit of a spread. And what we see here is for a given long wave feedback that the short wave feedback becomes more positive as the entrainment becomes greater. And I think that would mean more sensitivity. So, and this is, I think, consistent with seeing the water vapor and cloud feedbacks on the correlation diagram have the opposite sign. And then finally, water vapor feedback versus lapse rate feedback. We see that the lapse rate feedback actually gets more negative as the water vapor feedback increases. And again, there's this tendency for the entrainment coefficient to spread there, with the lower entrainment being associated with higher water vapor feedback, and then smaller lapse rate feedbacks when the entrainment gets larger. So there's a lot of control, and it goes down into fairly detailed aspects of the process interaction. And the reason I wanted to show this diagram at the expense of, it's a little bit laborious, is just to show the different ways in which entrainment in this model seems to be interacting with the important processes that control the climate feedback. So that was the story in the Hadley Center model. Now, just recently at GFDL, we've discovered, and it may be a little different how it works, but we've also discovered entrainment as a big control in our model. So the diagram here from Ming Zhao, we plotted climate sensitivity, and this time, for me, a little more rationally, the more sensitive ones go up instead of down on the diagram. So, and what we plotted against at first is the change in the cloud radiative forcing. There's a normalization there, but the change in the cloud radiative forcing associated with the perturbation to the climate system. So this solid line is showing, again, this absolutely, I think, pretty well accepted result that the spread in climate sensitivity is controlled by how strong the cloud feedbacks are. And that's what that bottom diagram is showing. It shows how much the cloud radiative forcing changes when we perturb the system. So that's the solid line, standard result. Again, sensitivity depends on the strength of the cloud feedback. But what's interesting, there's a whole bunch of experiments here indicated by numbers. Where are we on that line? How sensitive are we, and how strong is our cloud feedback? It turns out, at least if we lock the precipitation threshold, that we move down this curve fairly generally. There's one exception, it's a pretty small one. One and two are, those two experiments are pretty close. By increasing the entrainment coefficient in this model, we reduce the sensitivity. And we can produce a pretty wide range of sensitivities just by choosing the entrainment coefficient appropriately. So this is, I think, fairly important. At least we now are beginning to know in the climate model what controls the climate sensitivity, or what one of the major controls is, and that turns out to be entrainment. Now, again, it's a little strange that entrainment would be a control on this, given that low cloud response to warming is generally thought to be the big part of the climate sensitivity that's related to cloud change. So people are trying to explain that. These parameter studies, in a certain sense, are pretty mechanical. You take your climate model, you change the parameter, you see what happens. You don't understand why. So various ideas are out there. I'll just present one because it's gotten a lot of visibility. A couple of years ago, Steve Sherwood and Sandrine Bonny published this in Nature. And they wanted to argue that a big control on climate sensitivity is how effectively the lower part of the atmosphere mixes with overlying areas, because that's where the low clouds are. So if you can get the water vapor easily out of the boundary layer, that's going to change how easy it is for clouds to change when the system warms. So what they plotted here are climate sensitivity versus measures of how efficiently the atmosphere mixes in between the lower layer and the upper layer. So the first one is this quantity that they call S, and it's a function of the change in the relative humidity and the temperature between 700 millibars and 850 millibars. So it's lower troposphere mixing is the idea. And the way they define this is they argue that if lower tropospheric non-precipitating mixing were dominant, that this S value would be large. If you had no precipitation and the mixing were fairly shallow, you might expect that the relative humidity would go up because it's getting colder and there's no precipitation as those parcels go up, and the temperature would be dropping, so they have a minus in front of that. Deep precipitating convection, on the other hand, involves warm downdrafts between the clouds, so you'd expect the air arriving at 700 millibars in that case to be dry and warm, so that's going to make for a low S. And they looked at this index in the Indo-Pacific areas with a lot of deep convection and a few smaller ones where there's also some deep convection. And they found some evidence that, in fact, models that had a dominance by low mixing processes, high S, also had higher sensitivity. Those dots are a whole bunch of models from the CFMIP and CMIP 5 program. So there is some evidence there, although I wanted to point out GFDL doesn't play. These orange ones that are marked are all GFDL models, and we have the whole range of climate sensitivities, and we're straight line at best on their diagram. So the model structure here is important, and this is kind of a nuanced picture. They also looked at D, and D was their large-scale mixing, not the parameterized cloud type, but large-scale flow. It's just the ratio of shallow to deep overturning in these models. So again, large values of D are shallow mixing, and they tended, again, if you can look at it yourself and decide how convinced you were. If they added the two together, they thought maybe it made the case even a little more strongly. Again, GFDL doesn't play nice, but this begins to get at the question of how maybe convection and entrainment might be important for climate sensitivity through mixing processes that control how much water vapor is in the boundary layer where the clouds form. So if we have a big, large value of the entrainment coefficient, for example, we might think we're going to have shallow convection in that case, and their argument here would be that that's associated with a higher sensitivity. Of course, the GFDL model went the other way, so there's some questions about that. But the large-scale overturning also, if we have deep convection with low entrainment, maybe a stronger Walker circulation. So you can see these things being impacted by what goes on in the convection. So there's a remote connection, perhaps, between entrainment and deep convection and what happens with low clouds. So we don't yet fully understand this, but we're beginning to think about what might be going on and how that entrainment coefficient could, in fact, be the important control that it is on climate sensitivity. Okay, so
Doesn't it
yeah.
bother you that parameter D, which is like a shallow to deep of entrainment, is so much outside of observation?
Yes, okay, so good point, Murat. The models aren't doing very well with this. It bothers me, but it also tells me we're not doing the convection right, probably, in these models. I think that's actually, as part of the problem. The other concern on this is, so the diagram here, there are two analysis-based estimates on here, which I think are the square and the diamond, and it probably says somewhere on here even, I guess I didn't want, one of them is ERA and one is MERA. And then the black line are radiosondes. Even more disturbing, people like to trust analyses as being observations. The two analyses don't even fit the observational range.
These models in that metric within the range, but for D, they're just completely outside.
D is D. Oh, yes, exactly. Well, and this, I think that point is even more so than for the clouds. I would not trust something like the vertical velocities in any analysis after looking at that diagram.
So you know, the analysis is correct.
Yeah. But up here the analysis is failing to do the S. So do I trust it with the D? So I'm not sure. I would come out an agnostic after looking at this. I think I would say there's a plague on both houses. Probably. That's a good point. And again, a lot of this comes back to the diabatic heating, the convection, and the model, because these are all tied together. And it's now not at all surprising the sensitivity is up for grabs with this kind of fundamental, lack of coherence in the models at this point and lack of agreement with observations. So this points, where should we be going? Well, so I'm hoping one of the suggestions that maybe is coming out of this is that if we could, in fact, constrain one of the biggest controls on the deep convection, which is the entrainment, maybe we would make some progress on this. And so here's the point. Vertical velocities, of course, are correlated with entrainment. It's not the only thing. The microphysics is also important. I'll talk about that more later. But by looking at vertical velocities and comparing with the behavior of vertical velocities in models in convective plumes, we could maybe make some progress. But let's pick it up there, because vertical velocities at both resolved and unresolved scales in climate models have received little attention in the development of climate models to this point. Okay, parameterizations for clouds, convection and boundary layers, have been based mostly on mass fluxes, and that's been very powerful as far as it's gone. So EDMF, boundary layers, eddy diffusion, mass flux convection schemes like Arakawa-Schubert, they don't even do vertical velocity. So they don't even provide any information on it. They provide the product of vertical velocity and area, but that could mean anything from infinite vertical velocity at zero limit of area to much smaller values if the clouds are more extensive. So this is the next, let's get a little bit excited. This is maybe an open area where we can do something, and I think I've argued it's relevant to sensitivity and forcing. So that's the good news, and that's going to really be the last part of the seminar. Accurately simulated vertical velocities in climate models, and I hope to explain this a little more, appropriate treatment of their scaling properties when using them to drive aerosol and cloud processes could narrow uncertainty in both climate forcing and sensitivity. So that's kind of a theory modeling statement so far. But here's the other, when we look at transformative science, new observations are coming in. And that's the other piece which is absolutely essential. So new observations and advances in model resolution and parameterization offer prospects for this improved modeling. So we might actually be at a very good time in terms of making progress on these very long-standing and societally important climate change questions. Let me start out first by talking about resolved scale vertical velocities. So there are people building really powerful models, like S.J. Lin at JFDL and Murat, that we can maybe hope someday will be global in scale. And so maybe this ugly parameterization problem will just go away by having resolved vertical velocities. We're probably not too close to that yet. But clouds do form as a result of large-scale processes. And in higher resolution models, those resolved vertical velocities would be the ones that would go in, for example, to the ice formation and aerosol formation, and I should say liquid and ice activation schemes. But it turns out there's a problem here. It may actually be one that offers us some nice ways forward, though. What we're looking at here is a plot of observed atmospheric structure functions. This is from Cho and Lindbergh. It was published about 15 years ago. There was a campaign called Mosaic in the late 20th century. This were aircraft, and as they were flying, they measured the horizontal wind, both components, transverse and longitudinal to the flight direction. And what the structure function measures is how those wind components change as a function of distance. So you measure, pretty much right away from zero out to the whole flight path, and you ask what is the change in the horizontal wind as a function of distance along that flight path. And that change in horizontal wind through mass continuity will be obviously related to the vertical velocity, the average vertical velocity along that path, because if there's convergence or divergence, you have to have the air moving up or down out of that. So these show those structure functions. So we go from about, it looks like 2 kilometers or so up to over 1,000. And there's this rather robust, especially down here below about 100 or so, non-linear exponential behavior in the structure function. It's not linear. So what we can say is that there's a scale dependence there. It's nonlinear. And as a result of this, what we're going to see, because the vertical velocity is related to that by mass continuity, is that the vertical velocity in a model, if we could do what the atmosphere does, would depend on the resolution, and in a nonlinear way. So just by changing the resolution of a model, we're going to change the spectrum of vertical velocities in that model. If it's a perfect model, that's what would happen. And that means we will change the whole way that we calculate our cloud drop number, and indirect effects or aerosol perturbations depend very much on the base drop number. They're very strong when the number is small. They become less so when it's larger. So this is arguing, unfortunately, that if models do this, that our cloud-aerosol interaction depends on the resolution. Not a good situation to be in at all, obviously. Now, and the reality is that at least some models do this. And one of our best models, the European Center model, exhibits exactly this behavior. So Travis O'Brien and I are working on a perspective for nature on this, and Travis did this really nice calculation. He took this very high resolution T799 EC model, and basically, let's look at the blue curve. There's a lot of interesting stuff on here. The blue curve is, in this model, how the divergent component of the wind is depending on the model grid size, and he's dividing it by delta x. So let's look at that blue line. What we would expect from Cho and Lindbergh, they showed the square and they didn't divide it by x, but they would predict exactly this minus 2/3 power dependency on the resolution if the European Center model has the same scaling properties as the real atmosphere. And it does a pretty good job. The reference delta x 2/3 is that gray line. You can see Travis is showing a very nice agreement taking place there. The CMIP5, our climate model, CMIP3, CMIP5, I think these are actually the quartile ranges, but most of those models run right through that range where we've got that power law dependence on the vertical velocity. So if these all, I would say, used exactly the same aerosol cloud interaction approach and didn't have any subgrid issues, we'd be getting a range in forcings just because they ran different resolutions. Now, the good news about this is if we think very hard about what scale our parameterization should hold at, microphysics, the aerosol interaction schemes, what we could do is we could exploit this scaling to remove the scale dependence. And I think that's one of the things that we can do to move forward. But we have to be very aware that resolved vertical velocities have this scaling behavior, and that's going to be very important, the whole question of being scale aware when we build a climate model. Okay, so the next part of it, well, okay, let me just actually show it does make a difference. So my colleagues Bernard Vogel and Daniel Rieger at Karlsruhe did this calculation. They took one of the important cloud formation processes, which is heterogeneous freezing, and they looked at how the rate of ice particle formation in the model depended on the resolutions. They kept everything the same here except for resolution. They did this with the Icon Art model, which is a version of the Mox plot model that has been outfitted with very detailed microphysical and aerosol processes. And they ran it at resolutions as coarse as 40 globally down to nested with only 5. And so if we look at the diagram here at the begin on the upper left, they show the vertical velocities at which ice particles formed at models of different resolution, and this is pretty alarming from the scale aware point of view. You can see as the resolution changes that the vertical velocity the ice particles form at changes quite a bit. And remember that Jen Kay and Rob Wood diagram where there was this very strong dependence. And Jen and although they were looking at homogeneous aerosol, you might assume that there's going to be a similar problem for this. And indeed, these other diagrams show that. So what they did was they looked at these models and they kind of bootstrapped. So they compared their 40 with their 20 and so on all the way down eventually to their 10 with their 5. And they looked at exactly the same areas in those models. And they compared the number of particles that were frozen in the higher resolution in those in an area to the corresponding number in the large resolution. So you had more boxes in the finer resolution, took that mean number and compared it with what you got in the coarse resolution. And of course, it's very complex. This is what makes it hard to interpret observational data sometimes. Some areas got more ice, some areas got less ice. This histogram shows the exponent of the ratio of the number of particles and how it distributes. So blue were where you got less, red were where you got more. In all of these, most of the time, there's an increase between 1 and 10 in the number of ice particles, and it keeps building up all the way down, even here to 5 kilometers. So indeed, this kind of behavior has consequences for the cloud property, at least in this ICON art study. So this looks, really very central to the forcing problem. We need to use these scaling properties. And again, we might be able, the good news is the scaling has some robustness, so we might be able to use that to deal with this. But we have to think about this. This is clearly a very important part of the forcing problem. So those are resolved scale vertical velocities. Now, we're probably not going to have climate models that can do motions at the scale where a lot of the activation of ice and liquid takes place for a long time. The goal for climate models just after 2020 is they might have a 10-kilometer resolution. Marine stratocumulus clouds have large eddies 10 to 30 meters or so for typical motion scales. So we're going to have to deal with a big spectrum of clouds of different sizes that need to be parameterized. They can't actually be explicitly represented by the dynamical force, and even if they're represented by the dynamical force, I hope I just indicated there's issues even with that. So here's a picture showing the cumulus thing. The smallest of these might have a horizontal dimension under 1 kilometer. The big anvils get up to about 100. So these are the kinds of cloud systems where the activation actually takes place, and you can see below that even more like stratus-type cloud systems. So the argument I would make here is we need at least the PDFs of the vertical velocities to drive the aerosol activation process. The good news is this is starting to happen, but the approaches are not constrained adequately by observations of vertical velocity yet, but that's starting to change. So let me end on maybe a little bit of an optimistic note, and this is some of the work I've done myself on this. So I've constructed a cumulus parameterization that has in it, for a grid box maybe as big as what we're looking at here, even smaller, a spectrum of cloud sizes. So it tries to go from small to deep. And each one of those cloud types has associated with it an entrainment behavior. They have different entrainment coefficients, which means they have a vertical velocity. So the way that parameterization was developed was historically to use observations of vertical velocities from the GATE campaign in the 1970s. This involved aircraft flying through deep convection, and it was able to get only like the 4 to 8 kilometer average vertical velocity, and that's what we're looking at on this diagram. 4 to 8 kilometer average vertical velocities and a look at their PDF. So the observations there are the black open circles. That's what they saw during GATE. And I had an ensemble of plumes, convective plumes in my parameterization with basically a 1-parameter inversion problem. I assumed the entrainment coefficient spectrum might be universal, that it was always what it was in GATE. So I inverted that, and I had a pretty easy problem. It wasn't hard for my parameterization for GATE to match, and here's these purplish are my GATE plumes. The question always was, how valid was that assumption about universality of the entrainment coefficients. We couldn't answer it until about 2 years ago, and thanks to the DOE ASR program, which provided the observations and the postdoc to do this, we got an answer. So we looked at 2 cases where vertical velocities were observed. These same kinds of PDFs were observed from dual Doppler radar in the ARM program, and there were 2 campaigns. This is going to show 2 experimental cases in TWP ice that we looked at. And the observations there followed the blue line and the green line for those 2 different experiments. And there's a bit of a detection threshold question. So if I use the detection threshold of 1 meter per second over about a 5-kilometer layer, I think, that gave me one collection of data. If I moved it down to a half or up to 2, that gives me these spreads around those lines. Okay, so how did the parameterization do? It's the green and the blue. So if I wanted to be kind to myself, the glass is maybe 3/4 full. We're not off by that much, but there's some systematic errors occurring with respect to the strength or probably the buoyancy in those clouds. So another nice development, Yanggong Liu at Brookhaven has reformulated the entrainment coefficient behavior to depend on vertical velocity. So it looks like we've got a fix there based on recent theory and observation work. So, but in order to test that, we'll need other independent data. What's important here is these are completely independent data sets for checking this. Now we can look at it in a little more standard PDF type way, which this diagram does. The nice thing about the ASR observations, they're not just 4 to 8 kilometer averages, they're quite finely resolved all the way through the depth of the layer. So what we're looking at here is this TWP ice, these same 2 experiments, and we're looking at in red the strongest 1%, in green the strongest 5%, and the median in blue. Solid is what the model does, and open symbols are what the observations do. And you can see there's some dependence on height. We're at largest, except very, very near the top, we're within about a factor of 2 or 3 for our biggest errors on the strongest plumes. But we do have some tendency to be a bit strong in this independent TWP ice case. But there's also some dependence on, it's not always the same kind of behavior. For example, in the first experimental period, the strongest 1% were clearly too strong in the model. We're actually a little bit too weak in the model, so there's some spread around there. That we would expect as well. And we did this also for MC3E, which, so this TWP ice was Darwin, so kind of edge of a continent in the tropics, here to the mid-latitude of the US, and 3 cases in the MC3E campaign. Here, there's a little bit more evidence that the model is a little weak, at least at the strongest, and then it becomes a little too strong at the median. Again, for a first time, completely independent and a very naive assumption about entrainment, I would say the glass is 3/4 full, at least half. So the point is, we have a way to begin to tackle this problem, and with more work on it, work like Yanggong is doing on what controls entrainment, for example, we can probably improve on this. So I consider this to be an optimistic indicator. Things like the club parameterization, if those of you may have heard about that, for shallow clouds, that also predicts behavior of vertical velocities. And Yannuan Lin, who was a graduate of this program when he was an ARM fellow, started to look at that. We want to pick that up for shallow clouds. So actually, models are starting to do this, but it's new. But what's promising, this is something we hadn't done before. We've got observations to check it. We've got theory to suggest it's important. This is pretty promising. But there is some bad news here. If we're going to do this in a GCM well, we better hope that our highest resolution process models can do it, because those are what we like to refer to when we develop parameterizations. And right now, they're having some problems. So here we are back at TWP ice with work from Adam Barbel. The observations of the vertical velocities are the solid lines, and then a whole bunch of models, including Murat's SAM are in here, have had their vertical velocities analyzed, and they have kind of the same problem. This might make me want to have my 3/4 glass filled with something nice and spirited, because I could say I'm doing almost as well as the cloud models with this simple parameterization. They have a tendency also to over-predict the vertical velocities. So this is something that really needs to be addressed, and I'm very confident that that community, Murat and others, is going to be able to solve this problem. Ji-Wen Fen at PNNL has already pointed to one of the important issues, and that's the way the microphysics is treated in these models. Here again, we're looking at TWP ice, one of the experiments. Now the crosses are the observed vertical velocities, and she's broken it down in various ways. The two colored lines are both microphysics methods. More detailed so-called spectral methods that keep more track of how the particles of different sizes grow are in black. And I think the message that you're getting is it depends on the microphysics, and we start to do maybe even pretty well with that bin microphysics approach. So I think one of the things is for the cloud models to look at their microphysics. This does have case dependency. So here's an MC3E case where it didn't make so much difference what kind of microphysics you used. As usual things, there's no single silver bullet. Maybe a little better still with the spectral, but it's not as dramatic as that TWP ice case. And one more, here's another MC3. And now again, it looks like the bin microphysics is doing quite a bit better. So it looks like that's one of the important pieces.
Also,
yeah.
It allows for supersaturation.
That's one of the theories, yeah, that you can't get the supersaturation adjustment right. So if you think of your microphysics, the supersaturation equilibrium depends very much on the size of the drop. So if all you've got is just a drop number and a mass, which the bulk methods have, there may not be, and that's very nonlinear, you may not have the size. So that's one of the ideas. There are some other ideas out there as well. This is a solvable problem. That's why I'm actually pretty optimistic. When I show this, it's a call for action, a call for some research grants to be written. But I think this problem can be solved, and this microphysics is part of it. The other part that's important, I think, though, is the way turbulence is treated at small scales in the cloud model, because there's still a lot of stuff below the resolution limit. This is from Pete Bogenschutz and Steve Kruger. Let's just look at the bottom one, because things are running a bit late. What we're looking at here is work that was driven by Murat's SAM model. And the solid line shows SAM being run as, I'm pretty sure, yeah, this is SAM. The credit is appropriate to Murat on this. The LES version is run with 100 meters in the horizontal and 40 in the vertical, and that's the reference. We're going to call that the truth. And let's just look at the third moment of vertical velocity, these two bottom diagrams. Okay, so that's being compared with running this more like a cloud model, a pretty coarse resolution cloud model, 3.2 kilometers in the horizontal. And the different colors show different vertical resolutions going from 40 to 400. And at one idea, it was thought this was mostly a matter if you improve the vertical resolution, you do well on things like the vertical velocity in these models. Well, you don't. As you can see, even the 40-meter one, there's none of them are getting anything there. However, if you go to a different way of doing the turbulence, a higher order assumed distribution method, so club is an example of that. This actually used a much simplified version where some of the lower order, some of the less important terms were neglected. Now what you're seeing, the target, which is Murat's LES simulation, we're starting to hit that at coarse resolutions, even just 200 meters. So I think this is the other piece. Microphysics and turbulence in the cloud models will enable those to get the vertical velocities right, and hopefully they'll help people like me then do it on the parameterization issue. So let me wrap it up. There's been a lot here. Thanks for your attention. So we started out by noting that the observed climate transition from pre-industrial to present times depends simultaneously on climate forcing, sensitivity, and variability. I didn't talk about that one, but the precise determination of any of those from observations alone will not be possible unless we can at least make progress on either the forcing or the sensitivity. And again, this is very important for climate projections in the future because the masking by aerosol forcing will be reduced. We're going to really need to know the sensitivity to project toward the end of this century. Interactions between clouds and human-produced aerosols are a key source of uncertainty in climate models, so that's the forcing part of this. We could make progress on that. Maybe we could use the observations to pull out the sensitivity, for example. But cloud scale updraft speeds are a major control on that. Forcing is the point I wanted to make. So this is reason number one why vertical velocities are so critical. Next, entrainment and microphysics in convection are major controls on sensitivity in climate models, maybe in somewhat complex and confusing ways, but they both correlate strongly with convective vertical velocities. So here's a second, almost orthogonal way in which the vertical velocities could help on that sensitivity forcing, maybe they'll help us to get both, and we can pull out the variability. Yeah.
You never mentioned what this correlation is. Is it 0.9, 0.1?
So we saw it a little bit. I don't want to switch back at the end. We saw it a little bit on the diagram from the Hadley. So I'll switch back. I'll show that at the end, just when we finish. It's not the only one, but that's why I'm using correlate instead of cause. There are other pieces to this stuff, but I'll go back to that. Okay. Next, vertical velocities at both resolved and parameterized scales and climate models have received limited attention in climate model development. So this is something we can change. And accurately simulated vertical velocities and appropriate treatment of their scaling properties when using them to drive aerosol and cloud processes could narrow the uncertainty in both climate forcing and sensitivity. So I'll conclude there, and then I guess the first question has already been asked, so let me sit back and try to provide some insight on that. I don't know if we actually have, I don't think there's a correlation coefficient we can pull out. So in the GFDL model, for example, when the only thing that was changed was the entrainment coefficient in an experiment, we moved from about 0.9 for our climate sensitivity parameter all the way down to this 5. So there's a pretty big, that gives you some idea of how. No. So the, okay. No, sorry. You're asking a slightly different question. So the correlation with it, I would say it's one of two parameters that are primary controls on vertical velocity in a plume model. The other is microphysics. And roughly, I would say they're about equally important. So you've got to have it, is what it says. But you also have to have the microphysics. So I think that I would say that's not a correlation coefficient, because you might actually get a very small correlation coefficient just for that. But it's something you've got to have, and then you've got to do the microphysics as well.
I have a small follow-up, which is of a similar type.
Yeah.
Okay, let's just.
Oh, yes.
Okay. Thanks, everyone.
So, very, very interesting talk, very, very optimistic. In coming up with a number for vertical velocity for a particular scenario, what is the range of variations of vertical velocity across a cloud, and both horizontally and vertically,
Mm-hmm.
and also say with time? Right, so because here we see
yeah.
numbers for vertical velocity. So if I have an instrument and I go and measure vertical velocities at different places in the cloud, horizontally and vertically, and for 3 hours, then what is the variation around that?
Okay, so we'll get a little sense of that. So this gives you, this shows you the vertical variation. And the periods on these, for example, this one is over a 5-hour period. If we break it down, one of the cloud is obviously first starting to form, it's 0, so it goes up. I don't think the maximum values necessarily will be, this is the 1%. Maybe if you go down to an individual time, they'll be even somewhat greater. I don't really know what it would be if you sampled over just maybe a 15-minute period, or for that matter, over an area that's smaller than, say, this is, I think, down to the tens of meters scale. So they could push even a little bit higher than this. So that I don't know. So this is, at this point, actually, if we could get it to this level, I'd be pretty happy. But your question actually does remain important, because ultimately it is down at the scale of individual aerosols and droplets that we need to know. So there could be stuff going on even below the scale we've looked at here. But
it is which of these controls the sensitivity of cloud, because there's a whole lot of vertical velocity. So which of these controls climate sensitivity of climate?
Okay, so what I would say is, how accurate we're going to have to get this, I don't know. So the target right now would be, because an improper representation of the entrainment will give the wrong vertical velocities. If we can hit these, we'll be constraining the entrainment, and so that will move us forward on the sensitivity issue. So that's, I would say this would be a good starting target. I think if we could get down to this, we'll see where we are. And again, the baseline here is that we've really made almost no progress on this at all. But there is a good question. Just how much do we have to push it? That I don't know yet.
Yes, increase the entrainment usually reduce the vertical velocity, and in the meantime, probably reduce the efficiency from microphysics.
This is really let me go back to this GFDL diagram because that even has that. Oops. Okay. Well, it may not be that easy to bring this back. But yeah, you can trade off microphysics and vertical velocity. So what we're seeing from those aerosol diagrams, those aerosol forcing diagrams, is you need to use a pretty robust microphysics that no longer has those efficiency parameters in the miss-free choices. So if I had been able to get this to go back again, and I'm not sure that I can, what we are doing at GFDL in our AM4 model is there's a very simple two-plume convection scheme. And you can indeed both, the other important parameter is the precipitation efficiency. But as we go to the kind of microphysics that can support aerosol cloud interaction, that emerges from the microphysical theory, and it's no longer a tuning parameter. And when you get to that point, it will be critical to have the vertical velocity correct because you'll be locked in. Your efficiency will no longer be a choice. So the long-term program view on this is we get the vertical velocities and the microphysics both correct and get rid of this dreadful, we can tune either one and we can trade one off for the other. Because that right now, that's where we are. But the point of showing like those PDFs with the new AM3 parameterization is we're starting to get the vertical velocity, we hope, more robustly. And those could be constrained by the observations of vertical velocity. So then we'll have to get the microphysics right. We take out that other tuning parameters. So we get 2 for 1 on that. It's very powerful in that sense. But yeah, as long as you're playing a parameter game, you can tune it off. But I would argue that that parameter game is why we haven't made any progress on this, because we've been able to do that for the last 30 or 40 years.
Any other?
Yeah.
There are 2/3 structure functions associated with the triple cascade and the vertical subrating.
Yeah.
Tropic turbulence, right? So how would that apply to this situation?
Well, the one thing I haven't seen an explanation for yet is why observationally we see that power law dependence, because we would think at those scales we should be looking more like at quasi-dystrophic turbulence. So I'm not sure, so I don't at this point. This is a really good question. There ought to be a nice theory explanation. That's such a robust power law dependence. And of course, with power laws, sometimes you can get very different dynamics to produce similar power law behaviors. I don't know the answer to that question yet. It's an excellent one. And I think if we could, that theoretical understanding would be very powerful in terms of scaling, especially because the question I was a little vague on, I'm saying we could scale that down to where our parameterization is appropriate. Right now, when we build parameterizations, we don't really say there's a theoretical scale at which they should begin to apply. I mean, the microphysics, it should be somewhere where the velocity is, what the particles are seeing, but we haven't really said where that is. And you do have the situation that smaller scale 3D turbulence has a different kind of power law dependence than 2D. We know that in the atmosphere. So if we had a good theoretical understanding of where that scaling should stop, it could actually tell us maybe you have to get to that resolution to have a successful model. That might be attainable, and then your parameterizations need to match it. So that's a really good question, and I think we need to put a priority on answering that as a part of this idea that I'm promoting of using this information for breakthroughs. So, but I don't know at this point. But that looks too robust to me that there can't be something like what you're suggesting beneath it.
Okay, let's continue over the lunch hour and room 115. I really suggest graduate students, especially those who have their candidacy, to together there at 2 o'clock to ask you questions if you have those. Okay, let's.
Okay, thank you. Thank you. Yeah, I'm not sure how to. Yeah, well, we were far enough along that I think, and that's a good way to start making sure it comes from that. So, yeah.
So we have a.
The difficulty sounds like I would see whether I can set up a telecom whatever between YouTube and
Do you want us to just contact them directly?
You want to talk to him. Send me an email, let me talk, give him the number, then I'll try to talk to him and keep him in